Element 44, that's where we're at, and that is ruthenium. Welcome to Norris Teaches Science with me, Mr. Norris. This is a Physical Science Edition video, and it's in physics section of physical science. And today we're going to talk about thermal energy, which relates back to all the other energy videos I have done. So your goal for today's video is say, I can explain the components of thermal energy. So definition, what is heat? Heat is the transfer of thermal energy from one object to another object because of the temperature difference. Now, it's really important that you understand this, how heat flows. Heat flows from hot objects to cold objects, hot to cold, hot to cold. So think about it. You have a piece of ice in your hand. What's the hot object? It's your hand. The cold object is the ice. So heat is technically being transferred from your hand to the ice, not cold being transferred from the ice to your hand. The reason why your hand starts to feel cold is because there's an absence of the thermal energy there in your hand anymore, where the ice is sitting and have taken away your thermal energy. It's kind of how ice works in a glass. You have a glass of tea, you place ice in it. The tea is the hot object, the ice is the cold object. The thermal energy is transferred from the drink to the ice because the drink is losing thermal energy. That is why it gets cold. Now, what is temperature? It's the measure of how hot or cold an object is compared to a reference point. Most times we think of the reference point as being room temperature. And in America and North Carolina, where I teach, that's like somewhere between 70 and 75 degrees Fahrenheit as room temperature. Unless you're, say my mother who has it warmer, or my friends who have it at like 60 degrees Fahrenheit. I keep mine at about 75 when I'm up. At night, when I sleep, at 70. I digress. The thing is, when an object's temperature increases, the particles in there start to move faster and they expand. Think about going between a solid to a liquid to a gas to a plasma, what the particles look like. Now, there are three scales here. We have the Fahrenheit scale, which is America, Celsius scale, everywhere else, and the Kelvin scale is more of a scientific one, especially it's a positive numbers, and it deals with, high temperature stuff like the moon, like the sun. Now, the Kelvin scale, a little bit more about it. It's starts at 0 and it goes all the way up. It's all positive numbers, so there are no negative numbers on the Kelvin scale. And the reference point is 0 degrees Kelvin, also known as negative 273 degrees Celsius. We call that absolute zero. That's when this happens, matter does not move. Even solids, they vibrate a little bit. But when you're at absolute zero, they don't move. Good thing about it, we do not find it on Earth. Right? The easiest thing to know is that if you have your degrees Celsius, you add 273 to it, 73 to it, you have your Kelvin. That's how you convert this here. We're not going to talk about the conversion between Celsius and Fahrenheit because that is a lot of work. Now, what is thermal energy? It is the total potential and kinetic energy of all the particles in an object. Thermal energy depends on the mass of the object, the mass, the temperature, and what phase it's in. Is it in the solid phase? Is it in the liquid phase? Or is it in the gas phase? Thermal energy depends on all three of those factors. Now, when we talk about thermal energy, we have something called specific heat. It's the amount of heat needed to raise the temperature of 1 gram of material by 1 degree Celsius. And there is a formula to it. We're not going to do this formula, but there is a formula. Here's the thing. If something say you're comparing two objects, whichever one has the lower specific heat will heat up faster and cool down faster. So if you look here, gold has a lower specific heat than water, so it will heat up faster or cool down faster. Water, remember, if you don't remember from earth science, it heats up slowly and it cools down slowly. compared to, say, the land. So let's look at some examples of specific heat. It says a metal rod and a brick are both in the sun. Assuming that both are the same mass, which property of matter would make one hotter to the touch than the other? And the answer would be B, their specific heat, because they're going to be heated up in the sun. And it's all about the specific heat, how fast they heat up. All right, let's look at this one. The liquid in the two beakers have an initial temperature of 50 degrees Celsius and are left to cool. All right, so we have this one here has specific heat of 2400, and this one has specific heat of 4186. So the ethyl alcohol has a lower specific heat than the water. What will happen to the liquids? Well, if you look at your answers, remember it's all about specific heat. And the lower the specific heat, the faster heat up, the faster cool down. So the answer here would be ethyl alcohol will cool first. And when we also talk about thermal energy and heat and temperature and all this stuff, we have to talk about how we transfer thermal energy from one object to another. So the first one is conduction. This is the transfer of thermal energy with no overall transfer of matter. In a sense, you have to touch here. So I like to draw a picture when I do these. So conduction, I think of a hand that has too many fingers, doesn't it? A hand with an extra finger. Nope, it's got an extra finger. A hand. So you have to touch things. The thing is, conduction is best for solids. Solids. All right, convection. This is a transfer of thermal energy with movement of particles, and it's about fluids. The word fluid, if you don't remember, fluids from friction is liquids or gases. Liquids or gases, that's what it's going to work with. And so it's a transfer by circularization. So how I think about it, I think about arrow down, arrow up. All right, hot air rises, cool air falls. Hot air rises, cool air falls. When I lived in a third-story apartment building, when I first moved to where in the area that I live now, I lived on the third floor, and in the winter months, I didn't have to run my heat that much because all the heat from the apartments below me heated up my apartment. But in the summer, I had to run my AC a lot more because cool air falls. So the people at the bottom of the apartment, they lucked out and I had to run their AC as much. So my electric bill was more in the summer than it was in the winter. All right, and radiation is the transfer of thermal energies by waves through space. So I usually draw the sun when I think about this because the sun sends radiation out and that's how it heats the earth. But all things radiate energy or radiate thermal energy. If you have a light bulb on and then you get your hand close to it, don't touch it, but get your hand close to it, you can feel the thermal energy coming off of it. And the last thing about thermal energy is conductors versus insulators. A conductor is a material that allows thermal energy to transfer well. So it's really good for those conduction methods. And most of your metals are going to be good conductors of thermal energy. Insulators are materials that don't allow the thermal energy to transfer well. Think about insulation in your home. You want to keep your heat and keep the energy in your house. So think about that. It's like a blanket. Air's an insulator. Not all non-metal materials are it. Paper, cardboard, those are things that are good insulators. This is a little bit about thermal energy. I really hope you learned something today. Go find out more about thermal energy if you need to. Refresh yourself with some of the other energy stuff. And this is Mr. Norris, and I'll see you at the next video.